Now I am going to take up some questions based on principle of mathematical induction. Before taking up these questions, I will like to briefly discuss what do we mean by principle of mathematical induction. If a statement involving natural numbers is to be shown to be true for all n belonging to n, we generally use principle of mathematical induction. To make it simple, I have divided it into three simple steps. Step 1 is check that the result is true for n equal to 1. Put n equal to 1 in the given result and check whether it comes out to be true or not. Step 2 is assume that it is true for n equal to k. Put n equal to k in the given result and assume that it is true. Step 3 is prove that it is true for n equal to k plus 1. Now this is the main step. You have to simply write these two steps. For n equal to 1, check whether the result is true or not, and then put n equal to k and assume that this result is true. Real working is involved in step 3. We have to prove that this result is true for n equal to k plus 1 using this assumption. If we are able to prove these three steps, then by principle of mathematical induction, we can conclude that this result is true for all natural numbers. The logic is, suppose we check that the result is true for n equal to 1. Now result is true for n equal to 1. Take k equal to 1. Now since we have proved that if the result is true for n equal to k, it is also true for n equal to k plus 1. Assume that the result is true for n equal to k and prove that it is true for n equal to k plus 1. That is, it is true for the next natural number. Now we have checked that the result is true for n equal to 1. Now take k equal to 1. Now result is true for n equal to 1. It will be true for n equal to 1 plus 1, that is 2. So if it is true for n equal to 1, it will be true for n equal to 2. Now take k equal to 2. Now result is true for n equal to 2. This will imply that it is also true for n equal to 3. Again take k equal to 3. Now since we know that the result is true for n equal to 3, it will be true for n equal to 4 and so on. This is the logic behind the principle of mathematical induction. Now I take up the first question based on principle of mathematical induction. We are given A alpha is cos alpha sin alpha minus sin alpha cos alpha. And we have to prove that A alpha to the power of n is cos n alpha sin n alpha minus sin n alpha cos n alpha. Now, in principle of mathematical induction, what we do is, first of all, we check the result for n equal to 1. Then we assume that the result is true for n equal to k and then prove the result for n equal to k plus 1. First two steps are very simple and we simply have to write them down. In every question, for n equal to 1, step is very simple. For n equal to k, we have only to assume that the result is true. These two steps can be written directly. We have to exert only in step 3. Step 3 will involve the proof. So first two steps I write down. For n equal to 1, put n equal to 1 here. This is the result to be proved. N equal to 1, this is A alpha to the power of 1 is cos 1 alpha sin 1 alpha minus sin 1 alpha cos 1 alpha. Cos 1 alpha is cos alpha, sin 1 alpha is sin alpha, simple.
So what we see is A alpha to the power of 1 is, this is cos alpha, sin alpha, minus sin alpha, cos alpha. Therefore, n equal to 1, this is nothing but A alpha. Therefore, result is true for n equal to 1. We put n equal to 1 here and check whether this is true or not. But we are given A alpha is this much. So this result is true by given. Now for n equal to k, what we do is assume that the result is true for n equal to k. Assume that it is true for n equal to k. That is, put k instead of n. A alpha to the power of k is cos k alpha, sin k alpha, minus sin k alpha, cos k alpha. And the third step is to prove the result for n equal to k plus 1. That is, we have to prove that A alpha to the power of k plus 1 is equal to cos k plus 1 alpha, sin k plus 1 alpha, minus sin k plus 1 alpha, cos k plus 1 alpha. We have to prove this. These two steps are very simple and you can directly write them down. So now what we do is we have to prove this. So A alpha to the power of k plus 1. This is equal to A alpha into A alpha. A alpha to the power of k into A alpha. But A alpha to the power of k is known by assumption. Now in order to prove this, we will use the assumption. By assumption, A alpha to the power of k is known. This is known to be A alpha to the power of k is, this is the value of A alpha to the power of k. And A alpha is this much, or you can say this much. Now what we do is, we will carry out this multiplication. We multiply first row with first column, first row with second column. When we multiply first row with this, we get cos k alpha, cos alpha, sin k alpha, sin alpha, minus sin k alpha, sin alpha. This row with this column. So cos k alpha, sin alpha, sin k alpha, cos alpha. Now this row with this, minus sin k alpha, cos alpha, minus cos k alpha, sin alpha, this with this will give minus sin k alpha, sin alpha, plus cos k alpha, cos alpha. Simplification is cos A, cos B, minus sin A, sin B. Cos A, cos B, minus sin A, sin B is cos of A plus B. That is cos of k alpha plus alpha. This is cos A sin B plus sin A cos B. Formula is sin A cos B plus cos A sin B. Sin A cos B plus cos A sin B. So this will be sin of A plus B, that is sin k alpha plus alpha. This is same as this, only difference is of negative sign. Sin A cos B plus cos A sin B, if I take a negative out. So this will be minus sin k alpha plus alpha, and this will be again cos A cos B minus sin A sin B. So this will be equal to cos of k alpha plus alpha. Okay. So this is equal to now in 3, RHS is cos k plus 1 alpha, cos k plus 1, sin k plus this is this, this is this, this is this. So this is equal to R H S of 2. And you can write this is left hand side of 2. So left hand side of 2 is equal to right hand side of 2. Therefore result is true for n equal to k plus 1. Now you have proved all the 3 subjects. But you cannot leave the result here. You haven't made any conclusion. Now you say all the 3 conditions of principle of mathematical induction is satisfied, and therefore by principle of mathematical induction this result is true for all n belonging to n. And therefore we can say, therefore now we are applying the principle of mathematical. This line is very important. Therefore by principle of mathematical induction the result is true for all n belonging to n. That is, the result is true for all natural numbers. Natural numbers are nothing but positive integers. Therefore, result is true for all positive integers and hence proved. I now take up this next question. Let A and B be 2 matrices such that they commute. They commute means they are commutative. Commutative means A into B is equal to B into A. A and B are 2 matrices such that they commute. That is, AB is equal to BA. Show that for any positive integer n, AB to the power of n is Bn into A, and second part is AB to the power of n is An Bn. I will do one of these parts. I will take up the first part, and on similar lines you can try yourself part 2. So I am taking up part 1. Step 1 and step 2 are very simple. You simply write them down. Real working is involved only in step 3 when we prove the result for n equal to k plus 1. Now first of all what I do is I write up the first 2 steps and then prove the third step. Now we have to prove this result. AB to the power of n is Bn A, and we are given that A and B are commutative. That is, AB is equal to BA. We shall prove the result by induction. Now for n equal to 1, what we should have? AB to the power of 1, AB to the power of 1 must be equal to B to the power of 1 into A. That is, A, B to the power of 1 is AB, B to the power of 1 is B, BA. That is, AB is equal to BA, but this is given. Therefore, result is true for n equal to 1, which is true. The result is true for n equal to 1. You have to simply check that the result is true for n equal to 1. Now you assume it for n equal to k. Assume that it is true for n equal to k. That is, AB to the power of k is equal to bk into A. N equal to k, put n equal to k. AB to the power of k is equal to bk to the power of A. And we have to prove the result for n equal to k plus 1. Now for n equal to k plus 1, the result is A b to the power of k plus 1 is equal to b to the power of k plus 1 into A. We have to prove this result using this assumption. This is true, we have to prove that this is also true. Now I take up left hand side of 3. Left hand side of 3 is equal to A b to the power of k plus 1. This is equal to A into B k into B. Okay, and this is equal to, since associative law is true for matrix multiplication. So these brackets can be moved anywhere. So we will move these brackets from here to AB to the power of K into B. Associative law is true for matrix multiplication. Which law is not true? Commutative. But commutativity is given. So this is by using associative law. Associative law. Associative law holds for matrix multiplication. So this is equal to, now AB to the power of K is BK into A by assumption. So this is BK into A into B. This is from assumption to. Okay. By assumption, AB to the power of K is BK. So I have used AB to the power of K is BK into A. And this is equal to, now, associative law is again true. So what we do is B to the power of K into A, B. We have to prove that AB to the power of K is BK into A. So what I have to do is I will use commutative law and bring this B here. Then these two will get multiplied and we will get B to the power of K plus 1 into A. We have to move this B to this side. So what we do is B to the power of K into B, A. Because A and B are commutative using 1. A and B are given to be commutative. And then by using associativity, we can move this bracket from here to here. Because associative law for matrix multiplication is true. This can be written as B to the power of K plus 1 into A. B to the power of K plus 1 into A, and this is nothing but RHS of 3. Hence 3 is true for n equal to K plus 1. Therefore, the result is true for n equal to K plus 1. Therefore, we have carried out all the 3 steps of principle of mathematical induction, and now we can apply them and say that, therefore, by principle of mathematical induction, the result is true for all n belonging to n. I will briefly repeat the third step. We have to prove that AB to the power of K plus 1 is BK plus 1 into. So one thing is clear, that we have to interchange their sides. That is, we have to prove that A and BK plus 1 are commutative. So we have to change the sides of B and A. AB to the power of K plus 1 is A into B to the power of K into B. And from here, we know that A and BK are commutative, therefore these sides can be changed. So we are keeping in mind that we have to change the side of B. So here I have brought B here. AB and again B is brought here. So this is this and we get that. In these 2 steps, we are bringing B from right to left, from post multiplication to pre multiplication. AB to the power of K pKa, and then this, and again B is brought here. So this thing you must keep in mind while thinking about this question.
The next question I am going to take up is, let A be equal to this matrix, show that AI plus BA to the power of n is A to the power of ni plus NAN minus 1 BA, where A is the identity matrix of order 2 and n is a positive integer. Now, since we have to prove this result for all n, we shall prove the result by induction. Now, in induction, I have told you that it involves 3 steps. First, we have to check the result for n equal to 1, assume for n equal to k, and then prove for n equal to k plus 1. First 2 steps are very simple and we write them directly. For n equal to 1, we put n equal to 1 here. We get ai plus ba to the power of 1, a to the power of 1 I, 1 into a to the power of 1 minus 1 b a. And this is equal to a to the power of 1 is ai plus a to the power of 0. Anything to the power of 0 is 1. So we get ba. And therefore this is equal to this, which is true. Therefore the result is true for n equal to 1. Now we assume the result for n equal to k. Assume that the result is true for n equal to k. That is, this is true. Put n equal to k here. We get this. So we know that the result is true for n equal to k. And now we come to the third step, in which the working will be involved. These 2 steps are very simple. And real working is in step 3. Now, n equal to k plus 1. To prove that the result is true for n equal to k plus 1. That is, to prove ai plus ba to the power of k plus 1 is equal to a to the power of k plus 1 I. Put n equal to k plus 1 in this equation. Plus k plus 1 into a to the power of, now n is k plus 1. K plus 1 minus 1 will be k. This is k b a. So we have to prove this result. We start with the left hand side. LHS can be written as ai plus ba to the power of k plus 1 is equal to ai plus ba to the power of k into ai plus ba. And in proving the third step, what we do is we generally use the assumption. Now here, by assumption, ai plus ba to the power of k is this much. So we use the assumption here. From this equation, we will have a to the power of k, say this as 1, and we will say this as 2. So a to the power of ki plus ka to the power of k minus 1 b. Now by assumption, this is equal to this much, and we write this matrix as it is ai plus b. Now open this bracket. What we get is a to the power of k, and a to the power of k into a is a to the power of k plus 1, and this will be I into I is I square. This into this will be plus a to the power of k into b, ak into b. Scalar will get multiplied with scalar, and we will get I a plus. Now multiply this with this with this. So what we get is, first we multiply the scalars. k, a to the power of k minus 1 into a will be a to the power of k. And this is b, so b, and now the matrices will get multiply a into I. So this will be a I plus, now this into this. What we get is k a k minus 1 into b square a square. This will be k into a to the power of k minus 1, b into b will be b square, a into a will be a square. So what we get is a to the power of k plus 1, I square is I square is equal to I, and we get a k b I into a is a, definition of identity, plus k a to the power of k b a I is a, plus k a to the power of k minus 1 into b square a square, and this is equal to a k plus 1 I plus a k b is common, a is common, a k b a is common. So we get a k b, here we will get 1 plus a k b a is common plus k into a. I am writing a here. So plus k into a to the power of k minus 1 b square a square. So this is equal to a k plus 1 I plus a k b into k plus 1 a plus k into a to the power of k minus 1 b square a square. Now we have to prove this result. So what we see is this term is same as this term, and this term is same as this term. We are getting this term extra. Now how to tackle with this term? This term must be 0. So this is non-zero, this is non-zero, this is non-zero. So the logic tells you that you must evaluate a square. So evaluate a square, and a square will come out to be 0. A square is equal to 0, 1, 0, 0 into 0, 1, 0, 0. And this is equal to, now this into this, 0 into 0 is 0, 1 into 0 is 0. So this is 0. Now this into this, 0 into 1 is 0, 1 into 0 is 0. This term is also 0, and this is 0, so this will be 0, this will be 0. So this is 0. So a square is 0. So what we get is this is equal to a k plus 1 I plus k plus 1 a k b a plus 0 is equal to RHS. This is equal to RHS. Therefore, result is true for n equal to k plus 1. Hence, by principle of mathematical induction, it is true for all n belonging to n. That is for all positive integers. You must write this line. These three steps are true, and therefore we can apply principle of mathematical induction. And by principle of mathematical induction, we can conclude that this result is true for all n belonging to n. Now, We take up another question. A is equal to this much. Prove that a to the power of n is this much for every positive integer n. And you can try it yourself on similar lines. The topic I am going to take up now is transpose of a matrix. First of all, we define what do we mean by the transpose of a matrix. Let A be any m cross n matrix, then transpose of A is an n cross m matrix. If A is m cross n, then its transpose is n cross m matrix, denoted by A to the power t or A dash, and is obtained by interchanging the rows and columns of A. Mathematically, we can define transpose of A as let A be equal to Aij m cross n. Then A transpose is equal to Bji m cross m such that Bji is equal to Aij, such that Bji is equal to Aij. Now, since A is an m cross n matrix, therefore its row index will vary from 1 to m. So I will vary from 1 to up to so on m, and its column index j will vary from 1 to up to so on n. And here again j will vary from 1 to n and I will vary from 1 to m. And the relation for A dash to be transpose is Bji must be equal to Aij. I will illustrate it by taking an example. For a clear understanding, we will take an example. Let A be a 3 cross 2 matrix, general matrix of order 3 cross 2. Now we have to find its transpose. So its transpose A dash will be a matrix Bji of order n cross m, that is order 2 cross 3. So this can be written in short as A is equal to Aij 3 cross 2. If we want to write in this notation, then A is Aij 3 cross 2. Then A dash is Bji 2 cross 3. And this is equal to, now j will vary from 1 to, row index will vary from 1 to, and column index will vary from 1 to 3. So this will be B11, B12, B13. Now I will vary from 1 to 3. Column index will vary from 1 to 3 and row index will vary from 1 to 2. So second row will be B21, B22, B23. This is a 2 cross 3 matrix. Now definition says that Bji is equal to Aij, that is row and column index will be interchanged. So here this will become A1, 1, this will become A2, 1, this will become A3, 1, B1, 3 will be A3, 1. So this will be, here j is 2 and I is 1. J is 2, I is 1. 2, 1. So j is 2, I is 1. 1, 2. A, 1, 2. This will be A1, 2. This will be A2, 2. This will be A3, 2. And if we note from here, the transpose of A will be interchange the rows and column. So this column will become, first column will become first row. So A1, 1, A2, 1, A3, 1. Second column will become second row. A1, 2, A2, 2, A3, 2. So we get the same result. So these two definitions are equivalent. In mathematical form, we can define transpose in this form, and for understanding, we can define it in this form. Another example, for example, A is equal to say 1, 2, 3, minus 1, 0, 1, 2, 4. Then A transpose will be equal to, now this row will become first column. So this will be 1, 2, 3, minus 1. This will become second column. 0, 1, 2, 4. And we note order of this matrix is 2 cross 1, 2, 3, 4. 2 cross 4. And order of this matrix is 2, 3, 4. 4 rows and 2 columns. So if this is m cross n, then this is n cross m. I take up the first problem on transpose of a matrix. If Li, Mi, Ni, I is equal to 1, 2, 3 denote the direction cosines of three mutually perpendicular vectors in space, prove that A into A transpose is equal to I, where A is L1, M1, N1, L2, M2, N2, L3, M3, N3. Now, in this question, we will be using two basic results from vectors. So, first of all, I will tell you those results and then we will proceed with this question. Now, two basic results from vectors concerning direction cosines. Direction cosines. If alpha, beta, gamma are the angles made by a vector OP with the coordinate axis, positive direction of coordinate axis OX, OY, OZ, positive direction respectively, then its direction cosines are cos alpha, cos beta, cos gamma. If a vector OP makes angles alpha, beta, gamma with the positive direction of coordinate axis OX, OY, OZ, then its direction cosines are cos alpha, cos beta, cos gamma. Alpha, beta, gamma are the angles made by OP with these axes, then direction cosines are cos alpha, cos beta, cos gamma, and sometime also denoted by L, M, N. And L square plus M square plus N square must be equal to 1. That is cos square alpha plus cos square beta plus cos square gamma must be equal to 1. This property must be satisfied if L, M, N are the direction cosines. Now two vectors OP and OQ having direction cosines L1, M1, N1 and L2, M2, N2 respectively are parallel if and only if L1 over L2 is equal to M1 over M2 is equal to N1 over N2, and they are perpendicular if L1 L2 plus M1 M2 plus N1 N2 is equal to 0. That is, their dot product is 0. L1 L2 plus M1 M2 plus N1 N2 must be equal to 0. So you must remember these two results. For parallel, L1 over L2 is equal to M1 over M2 is equal to N1 over N2, and for perpendicular, L1 L2 plus M1 M2 plus N1 N2 must be equal to 0. So with this basic knowledge about direction cosines, we come to the main question. So in this question, we are given the matrix A is equal to this much. And we have to prove A into A transpose is I. Now, A is equal to this much. And its transpose is change this column into first row. First column into first row. So this will be L1, L2, L3. Second column will become second row. M1, M2, M3. Third column will become third row. N1, N2, N3. And we have to find the product of A and A transpose. Therefore, A into A transpose is equal to A is this much, A transpose is this much. And we have to find the product A transpose. Now, matrix multiplication is a row column multiplication. So, first row will get multiplied with the first column. First row with first column. L1 square plus M1 square plus N1 square. First row with second column. L1, L2 plus M1, M2 plus N1, N2. We get this entry. L1, L2 plus M1, M2 plus N1, N2. First row with the third column. L1, L3 plus M1, M3 plus N1, N3. Now this with this will give L1, L2. L1, L2. This with this. So M2, M1, M2, M1, N2, N1, N2, N1. This with this. L2 square plus M2 square plus N2 square. L2 square plus M2 square plus N2 square. This with this. L2, L3, L2, L3 plus M2, M3 plus N2, N3. And similarly this with this. L3, L1 plus M3, M1 plus N3, N1. This with this. L3, L2, L3, L2 plus M3, M2 plus N3, N2. This with this. This will be L3 square plus M3 square plus N3 square. So we get this matrix. Now in direction cosines, since L1, M1, N1 are direction cosines of vector, therefore L1 square plus M1 square plus N1 square must be equal to 1. This must be 1, this must again be 1, this must also be 1, because L2, M2, N2 are direction cosines, L3, M3, N3 are also direction cosines. So this must be 1, this must be 1, this must be 1. Also, since these three vectors are mutually perpendicular, therefore L1, L2 plus M1, M2 plus N1, N2 must be 0. This must also be 0 because vectors are mutually perpendicular. This must be 0, 0, 0, 0. So we get the matrix. This is 1, this is 0, this is 0, this is 0, this is 1, this is 0, this is 0, this is 0, this is 1. So this is equal to I3. Now I take up the next question. We are given the matrix this which satisfies the condition AA transpose is equal to 9I3. If A is equal to this is a matrix satisfying AA transpose is 9I3. That is, this matrix satisfies this condition. Then we have to find A and B. So what we do is A into A transpose is equal to 9I3. So this implies A is, how much is A? A is this much, and A transpose is, interchange the rows and columns. What we get is 1, 2, 2. First row will become first column, and second row will become second column. 2, 1, minus 2. Third row will become third column. So this is A transpose, and this is given to be 9I3. 3. That is 9I3. I3 is 1 0 0 0 1 0 0 0 1. Now matrix multiplication is a row column multiplication. So we multiply this row with this column. What we get is 1 into 1 is 1, 2 into 2 is 4. 1 4 4. 1 plus 4 is 9. Now this into this. 2 plus 2 minus 4. 2 plus 2 minus 4 is 0. This into this. This is A 4 2B. A plus 4 plus 2B. A plus 4 plus 2B. This into this. What we get is 2 plus 2 minus 4. 2 plus 2 minus 4 is 0. This into this. 2 into 2 is 4. 4 plus 1 is 5. 5 minus plus 4. 5 plus 4 is 9. This into this. This is 2A plus this into this is 2. This into this is minus 2B. Now this into this. A plus 4 plus 2B. A plus 4 plus 2B. Now this into this. This is 2A plus 2 minus 2B. 2A plus 2 minus 2B. This into this. This is A square plus 4 plus B square. A square plus 4 plus B square. And this must be equal to, now multiply each and every entry by 9. So we get 9 0 0 0 9 0 0 0 9. And for equality, the corresponding entries must be equal. So 9 must be equal to 9, 0 is equal to 0. This must be equal to this. So we get the equation A plus 4 plus 2B is equal to 0. This should be equal to this. This should be equal to this. This should be equal to this. So we get another equation 2A plus 2 minus 2B is equal to 0. And from here we get A plus 4 plus 2B must be equal to 0. From here we get 2A plus 2 minus 2B should be equal to 0. That is 2A plus 2 minus 2B is equal to 0, which is same as this. And last equation we get is this. That is A square plus 4 plus B square must be equal to 9. So this implies A plus 2B should be equal to minus 4. And this implies, now 2 cancels throughout. So we get A minus B. This is A minus B is equal to minus 1. And this is same as this. And this is same as this. So we get one more equation. From here we get A square plus B square is equal to 5. So we get these three equations, 1, 2 and 3. Now we must solve these three equations simultaneously. From these two we will find A and B. But this equation must also be satisfied. So from these two equations, when we get A and B, then we must check that those values of A and B should satisfy this equation. Then it will be a solution, otherwise it will not be a solution, because all the three equations must be satisfied. So from 1 and 2, what we get is 1 minus 2. 1 minus 2 implies subtract 2 from 1. These two cancels and this will be plus. So we get 3b. 3b is equal to minus 4 plus 1, that is minus 3, and this implies b is equal to minus 1. Now substitute b here, so 2 implies a is equal to b minus 1, that is equal to minus 2. So a is minus 2 and b is equal to minus 1. Now substitute these two values in 3. Substituting in 3. So what we get is a is equal to this. So minus 2 square is 4 plus minus 1 square is 1. This is equal to 5. Satisfied. Therefore, this is the solution. Therefore, a is equal to minus 2 and b is equal to minus 1. Answer. If these two values don't satisfy this, then we will say that this is not a solution. And the answer would have been no solution.